We have a mixture of topics today. Most of today is going to be continuation of our examination of hashing, but I had one thing to finish up from Monday. We were analyzing balls and bins, if you remember, and we were looking at the sort of remarkable things that happen with the power of two choices. And I showed you this very interesting, the intuition behind the power of two choices is very straightforward, that basically the probability of having your ball choose two heavily loaded bins is the square of the probability that it will choose one, which makes it very small. And so most balls pick a lightly loaded bin, and so this keeps all of the loads small. But we had to wrestle with dependencies, right? There was the dependency of, what bins are tall depends on what happened to the balls that came before me. And so there isn't sort of an elegant closed form for the exact probability that my ball is choosing two low bins. And so we had to upper bound that, and we had this very nice coupling argument that allowed us to say that even though there's this weird dependence, the number of balls that pick two tall bins is stochastically dominated by a simple binomial distribution, and so we can apply the Chernoff bound to it. And so we showed in particular that, where are we in the notes? Yes, we defined sort of VH to be the number of bins, or is it the number of balls? Let me be careful with my notes. Yeah, to be the number of bins of height at least h. We know that V4 is less than or equal to n over 4. That's our base case, right? And then we started looking at these variables for a particular stage to consider height 5, or sorry, we generalized it, so I'll use the generalization. To consider height h plus 1, what we said was that if we suppose that VH was less than or equal to some beta h times n, then we could conclude that the expected value of V sub h plus 1 was less than or equal to beta h squared times n. And we used this coupled Chernoff bound to say that the probability that VH plus 1 was more than twice its expectation was negligible. This was just using epsilon equal 1 in our Chernoff bound, which was less than or equal to 1 over n squared when the expected number of tall bins was larger than 2 log n or so, right? And we then showed that this gave us a recurrence for the beta h's and let us prove that 2 beta sub h plus 1 can be set equal to 2 beta h squared in this recurrence, which gives us a bound of beta h being 1 over 2 to the 2 to the h plus 1. So we have this double exponentially decreasing beta h's because they basically keep squaring. There's an extra factor of 2 coming in, but it's swamped by the fact that the numbers keep squaring, right? So this was nice, but there is still a dependence that we have to worry about. There's also the sort of the very end, where the expected number of tall bins is very small, and the Chernoff bound is no longer hitting as strongly. The Chernoff bound is no longer as small enough to let us progress. So I have to finish that up today. But are there any questions about where we're starting? No? Okay, so looking at this analysis above, let QH be the event that V sub H is less than or equal to beta H times N. Okay? These are the events that we want to have. This is what we're hoping is actually true for all the different values of H. That none of the, that for each value of H, there aren't too many tall bins. Okay? But we now need to look at how these different layers of analysis interact. Okay? So the easy part first. So suppose that Q4 holds, which we know it does, deterministically, right? And that the probability of Q sub H conditioned on Q sub H minus 1 is greater than or equal to 1 minus epsilon. So this is basically what we proved above, but I'm going to have to be careful. So I will be careful in a minute. But if we're able to prove this, right, that conditioned on not having too many height H minus 1 bins, we also don't have too many height H bins, right? And suppose this holds for all epsilon. Well, then I can conclude that the probability of QH is greater than or equal to the probability of QH and QH minus 1, since that's a strictly smaller event, which is the probability of Q sub H given Q sub H minus 1 times the probability of Q sub H minus 1, which is, I can ignore the second term. Sorry, this is at most 1. And so if we have this conditioning, then basically by induction, we can conclude that, whoops. There we go. We can conclude by induction that all of the QHs are reasonably likely. Another way to look at this is to just say that this is an upper bound on the probability, or a lower bound on the probability of all the QHs, right? You can write out this big QH and QH minus 1 and QH minus 2 and so on all the way down to Q4. And now you can expand this out as a chain of conditional probabilities, and each of the steps in the chain is bigger than 1 minus epsilon, so the product of all of them is bigger than 1 minus epsilon to the H, right? So basically, as long as we have a likely count for height H bins conditioned on height H minus 1 bins, we have a likely count for all the different height H bins, right? But it remains to prove this thing that I'm claiming up here, right? That probability of QH given QH minus 1 is at least, is very large, okay? And we didn't actually quite prove that in our analysis above, because there's still some conditioning that we have to worry about, okay? The problem is that we only know if QH minus 1 holds sorry, let me do this. I'm going to be talking about QH more than there. We only know QH plus 1 holds after all the balls are placed. Right? So we're thinking about conditioning on various events. We're saying, you know, we want it, whoops, we only know QH holds after all the balls are placed. So we want to talk about the probability of QH plus 1 conditioned on QH. Well, we can condition on QH, but if we're conditioning on QH, we kind of said we put down all the balls, and now we know that there aren't too many height H bins. Okay? But at this point, we've put down all the balls. So how can we analyze the number of height H plus 1 bins? So there's an intuition problem, because in a sense, we want to condition on the future. Right? We want to talk about placing one ball at a time and think about whether it's too high or not. But the event we're conditioning on, so that we can do this chaining of events, is an event that's determined in the future. So we are conditioning a present event on the future. And mathematically, there is absolutely nothing wrong with this. But it hurts your brain, right? And it's hard to know if you're proving things correctly. Right? It's hard to describe the distribution that arises on what happens to a ball you're placing now if you're conditioning on a future where there aren't too many tall bins. Okay? So we're going to be a little bit careful to change our conditioning so that we're only conditioning on the past, and so that our proof can seem natural. So how are we going to do that? Okay. I'm going to use some notation from last time. Remember that I had this variable yt, which is equal to 1, if ball t has height at least h plus 1, which means that it's contributing to a height h plus 1 bin. Right? With this definition, I know that the number of height h plus 1 bins is less than or equal to sum of yt, right? Each of the height h plus 1 bins has to have a height h plus 1 ball in it. Okay? We want to bound this sum of yt's conditioned on not having too many height h bins, which is this weird event in the future. Okay? So how am I going to get around that? What I'm going to do is I'm going to write a slightly different variable, yt prime, which is equal to 1, if yt is equal to 1, and the number of tall bins at the moment that I am inserting the teeth ball is less than beta h times n. Okay, so remember, this is our target. This is the thing we want to assume about the previous bound. But now we're not assuming that the final number of tall bins is less than or equal to beta h n. We're just assuming that the number of tall bins at this moment is less than or equal to our target. Okay. And so this is an event that doesn't reference the future at all, right? So this depends only on the past. So we can use our principle of deferred decisions to analyze what's going on. The probability that yt prime is equal to 1 is equal to the probability that yt prime, I won't write equal 1 anymore because it's just an indicator variable, given, I'm going to write this as qh of t minus 1, adding a time index on the event of not having too many tall bins, right, times the probability of QH of t minus 1. Right? But this is less than or equal to 1, of course, so I'm just going to ignore it. This is less than or equal to the probability of this event just conditioned on the not having too many bins. Right? But again, this is an event that's asking about the teeth ball conditioned on what happened with the previous t minus 1 balls. It's a nice normal conditioning on the past. This is less than or equal to beta h squared. Yes? Because there's only beta h times n balls of height h. And so the probability that our teeth ball picks 2 of them is beta h squared. Okay. So these yt prime fit the stochastic domination lemma from last time. Right? Remember that stochastic domination lemma said your y's are supposed to depend on the previous balls only, right? And even though they're not entirely independent because they depend on exactly where the previous balls landed, you have this upper bound of beta h squared, so you can treat it like a binomial distribution and you can apply the Chernoff bound. Okay. So immediately we can apply the Chernoff bound from last time. We know that the sum of the yt primes is less than or equal to 2 beta h squared n, which is beta h plus 1 n times n with high probability. Okay. So why did I introduce these yt primes? Well, they're kind of providing an escape hatch, right? So the yt's, you're trying to condition them on this weird event in the future. And so it's hard for you to understand what the probability of these yt's is looking only at events in the past. You need to figure out how to condition on the future, right? By incorporating this extra term, right, I've just made something which is less likely than the yt's, right? But also something that I can bound using standard conditioning. Okay? Now, how do I use these bounded variables? Well, now note the next step. If QH holds, then every QH at t minus 1 at t holds. So in fact, all the yt's are equal to the yt primes. And the sum of the yt's is equal to the sum of the yt primes. Okay. Which means that the event of QH and sum of y prime t greater than or equal to beta h plus 1 n is the same event as the event of QH and sum of yt is greater than or equal to beta h plus 1 n. And so they have the same probability. Okay. So because I'm only interested in the part of the event space where these two sums are the same, they're going to break their bound with the same probability. Okay. And now I can conclude that the probability that QH holds, but QH plus 1 does not hold. So I'm working on proving this conditioning that I need so that I can repeat the argument level by level. This is just a different way of writing the conditional probability that I'm interested in. Is equal to the probability that QH holds, and it is not the case that VH plus 1 is bigger than beta H plus 1n. Which, as we argued at the top of this, at the top of the upper board, is less than the probability that QH holds and the sum of the YTs is bigger than beta H plus 1n, because the sum of the YTs upper bounds VH plus 1. Which is equal, because I just argued that these two events are the same, that the probability that QH holds and the sum of the YT primes, sorry, this shouldn't be a not, right, is bigger than beta H plus 1n. But this is a conjunction, so I can ignore one of the events and still upper bound the probabilities. But again, the author has sort of cleverly defined these YT primes where, like, again, what we're looking at is we're worrying about balls not being not too high, and we had all this conditioning going on. But YT prime included the condition we care about in the indicator variable. And that means that we can talk about the YT primes having low probability without any conditioning at all, right? The YT primes are just unlikely to happen, right? So here we have something about these YT primes, which do not have to be conditioned. And so we showed, using the Chernoff bound, that this was very small. Okay. So, now I have to finally get back to the conditional. So on the previous board, I gave a bound of a conjunction bound. Now I just need to relate the conditional probability I care about to it. So the probability that I get too many H plus 1 bins when I don't have too many H bins is equal to the probability that I get too many QH plus 1 bins and don't have too many QH bins divided by the probability that I don't have too many H bins. Okay. But we just argued that this was less than 1 over n squared by a Chernoff bound. By the same reasoning, this is bigger than 1 minus 1 over n squared, right, by induction. So what we have here is 1 over n squared times 1 minus 1 over n squared, which is still about 1 over n squared. Okay. We lose a little bit, but we're only going log n levels, so the little bit that we lose is negligible. Okay. So now that I've got it all on the board, let's look back at sort of the clever subtleness of this analysis, right? we wanted to bound the probability that a certain sum of random variables was large, the sum of yt's, conditioned on this event in the future. That's hard. So we defined a different set of random variables where we don't have to condition on the future because we've brought a condition into the random variable to make sure that even if weird things are happening, like this definition is basically saying, well, if things are going according to plan, then yt prime is going to be small because of our stochastic domination argument. If things are not going according to plan, then yt prime is going to be 0. So either way, according to plan or not according to plan, yt prime is small. And that lets us apply, or yt prime has small expectation. And that lets us apply a Chernoff bound to the sum of the yt primes. But then we go back and say, well, the yt primes are different from yt's when when things are not going according to plan. But we're going to use induction to argue that at each step, things are still going according to plan, so that the yt primes are actually equal to the yt's. And therefore, our analysis of the yt primes also gives us a bound on the yt's, and that lets us take the next inductive step to get the next height argument. Okay? So as I said at the beginning of the Monday lecture, what we have here is an incredibly simple and intuitive technique with a super subtle, complicated analysis, right? And what's great about that is that the people implementing this don't have to understand the analysis. They can just use this incredibly simple technique, right, and know that it works, and leave it up to the theoreticians to actually have done that proof. So there's only one little thing left to do, the last few stages. Right? So there's a certain height h where the number of balls that we get is about order log n. And the problem is, at that point, we can't, like the Chernoff bound is exponential in the number of balls that you expect to get. So if the number of balls gets smaller than this, you can no longer say that with high probability you're only getting a few bins, right? But the point is that at this point it's actually easier, right? At this point, the probability of a height h plus 1 ball is log n over n squared. Right? We only have log n or so height h bins. So the probability that you hit 2 of them is tiny, right? So the probability that 2 distinct balls both end up at height h plus 1 is at most, well, what's the probability that a single ball gets height h plus 1? Log n over n squared. So the probability that 2 balls both get height h plus 1 is the square of this, right? Log n over n to the 4th, right? But that means that the probability that any 2 balls end up at height h plus 1, how can I bound that? Yeah? Union bound, right? There's only n squared pairs of balls. So this is whatever, log to the 4th n over n squared. So with high probability, you only have one height h+1 ball. Right? You have to do the same sort of stochastic domination argument to get rid of dependence as we did when we were using the Chernoff bound, but the argument goes the same way. Yes? Well, there's n squared pairs, so you're going to have, right. Right, so if you're trying to apply a union bound to your n squared pairs where the probability of a pair is... Oh, I see what you're saying. So let's see. Yeah, I think you can. Let's see. I think you're right, but I'm scared of saying things like that in class and turning out to be wrong later. Okay? But this is definitely right because I checked it. So in any case, only one height h+1 ball. And if there's only one height h+1 ball, then there's only one height h+1 bin, which means that it's impossible to have a height h+2 bin, right? Because the ball would have to pick two separate height h+1 bins. So that's the end of the story. Okay. All right, and I talked last time about going to D choices and sort of breaking symmetry to the left and so forth, so I won't repeat that now. But now we've completed the analysis. We've taken care of all of the subtle dependencies that get in the way of proving the correctness of this bound. Okay. Any questions? All right. This probably didn't all make sense. It took me a few years of lecturing it for it to really make sense to me. So I encourage you to take another look at it with the notes, so that, because again, like, the analysis of randomized algorithms is where the complexity shows up, the mental challenge. And it's good to get familiar with these sorts of arguments because you will be using them frequently. Okay, so now switching topics, moving on to hashing. We had a recorded lecture on Wednesday which covered universal hashing and perfect hashing. And I wanted to check if there were any questions about that before I moved on. No? I expected many of you to have seen that before, so I thought it was a good one to throw into a recording. What I'm going to show you now is a couple of more advanced / weirder hashing techniques. Now, in order to keep the analysis of these more advanced hashing techniques from getting too complicated, I'm going to make an assumption which can be justified, but I'm not going to bother. I'm not going to do the work. Which is just that your hash values are random and independent. Okay, I'm going to use these hash values in weird ways, and that's what I want to focus on. And I don't want to talk too much. So we saw with true universal hashing, the whole idea was you wanted to assume that the hash function, the items were being placed in random independent locations. That takes too much randomness. It's hard to compute. So we use pairwise independence in order to get enough randomness in the placement for our analysis to work. Okay, but the analysis that we started with was basically about independent random placement. And then we just made this argument at the end that we didn't need full randomness. I'm going to be taking the same approach here. I'm going to be assuming full randomness in the analysis. And fortunately, other theoreticians have done the work of showing that you don't need full randomness in order for this analysis to work. It's enough to use some kind of limited independence. Okay? So the first thing that I'm going to show you is something called cuckoo hashing, which is a really cute, practical hashing technique for keeping worst case loads, worst case lookup times small. Okay. And it's actually another sort of interesting application of the two choices idea. And it may have been inspired by the two choices idea, I'm not sure. So normally when we hash, we have an array of size n, and we hash our items into the array of size n, but we have to worry that multiple things get hashed into the same location in the array, right? And so we did 2 universal hashing in order to keep the number of items small. We did perfect hashing in order to keep the number of items below 1 in each location in the array. But it got pretty complicated, that perfect hashing. You needed these 2 levels of buckets, and you needed to rebuild, and so on and so forth. So the idea of cuckoo hashing is to use 2 arrays of size n. So that you have 2 choices. Okay. To hash an item, okay, hash it to each array. So this gives you 2 chances to find an empty bucket. Okay. Oh, and so n here is going to be the target number of items that we want to store in the bucket. But I'm going to use m for the number of items that we store so that I can talk about what happens as you vary m. Okay, but you should think about trying to put about n items into your 2 arrays of size n. All right? So to hash an item, you hash it to each array. And basically, if either is empty, you're done. You can put your item into that location. Okay. But you have a problem if both of the locations are full. Okay. What should you do if both of the locations are full? Well, you should think like the cuckoo bird. Do people know about what the cuckoo bird is famous for? Oh, you haven't done your bio gen ed yet? Yes? Exactly. The way the cuckoo gets its eggs taken care of is that it lays them in another bird's nest, and it pushes that bird's eggs out. So that bird ends up taking care of the cuckoo's eggs instead. Okay, so with that context, what do you think we should do if both of our buckets are full? Yes? Well, I already told you the 2 things that this item hashes to. It has to go to one of them. So what should I do? Yeah? Oh, sorry, is that a hand? I couldn't tell. Go ahead. Exactly, right? Else, put in one of my spots and evict the item that's there. What does that item do? Well, it has 2 locations, so it goes to its other location. And if necessary, it evicts what's there, which goes to its other location. And so on. Right? So this is also that old nursery rhyme about how there were 6 in the bed and the little one said roll over and they all rolled over and one fell off. And if you're familiar with that nursery rhyme, right? So essentially, new thing comes in, and if necessary, it evicts an old thing which moves to its other location, which may evict something else, and you get this chain of evictions. And if things go well, eventually that chain of evictions will lead to an item moving to its other spot which is unoccupied. And then you're done, right? And you've successfully placed the new item into the buckets. Okay? And so what's nice about cuckoo hashing is that there is at most 1 item per bucket. It is a kind of perfect hashing scheme. that you, or almost perfect hash, because you need to, if you want to look up an item, you look in exactly 2 locations, and either it's there or it's not, right? So lookups are constant time, just like in perfect hashing, but without the whole complicated 2-level stuff. A question? Yes, so pretty much all hash table analyses sort of make this assumption that there's some bound on the number of items, and you what's the word I'm looking for? You provision your hash table to hold that number of items. And if the number of items grows to exceed what you have provisioned for, then you need to grow your hash table in some way. And the easy thing to do is some kind of repeated doubling scheme, that when you approach full, you double the size of the hash table, and you start over, and you reinsert everything. And you can prove with these repeated doubling schemes, I mean, I think I had you do this in your homework, that the cost of all the reallocation is amortized constant. Okay? Now, in some situations, amortized constant is not good enough. You have real-time applications, and you don't want them to hang while you're doing some big reallocation. And so there are techniques, there's something called dynamic perfect hashing, for example, where you can actually do the reallocation slowly as the items arrive so that you don't have to do one gigantic reapportionment. Okay? But for this analysis, let's just assume that, you know, I've got this hash table, 2 size n arrays, and it's going to be happy until you insert too many items, and then it will explode, and you'll have to start a new hash table. Okay? Other questions? Okay, so what can go wrong in cuckoo hashing? Yeah?
You could enter like an infinite loop, right?
Yeah, what would that infinite loop look like?
Everything's full, then you're like, you evict, and then they evict, then you keep going down.
Does it require everything to be full?
No, you could actually, I guess, like, if, say, you were unoccupied, and then you evicted something else, then its other spot was like one of those same spots.
Yeah.
Okay.
Yeah. So there's actually a very elegant way to model what's going on so that we can make pictures of the problem. So if I draw my 2 arrays, each item that comes in has one location on each side. I'm just going to draw a line between them. Okay. So for each item that comes in, I draw a line that connects one bucket on one side to one bucket on another side. What am I making? Yes? I'm making a graph. In particular, I'm making a bipartite graph, right? And also, very importantly, each edge is a random edge. Right? Because it has a random left endpoint and a random right endpoint. Okay? So, fortunately for us, random bipartite graphs and also random non-bipartite graphs have been a subject of intense study for decades. And we know all sorts of beautiful, amazing things about the nature of these graphs. And you can take, there are entire textbooks on the theory of random graphs. This theory was initiated by 2 really important combinatorialists, Paul Erdős and Renyi, whose first name I've forgotten. Paul Erdős is one of the truly incredible figures of randomized algorithms. He would hate to be called an incredible figure of randomized algorithms because he considered himself a mathematician. One of his famous sayings was that a mathematician is a machine for turning coffee into theorems, and a computer scientist is a machine for turning coffee into urine. So that was his take on us. But he proved He has published a terrifying number of papers with a terrifying number of collaborators. And if you go on the internet, you can find pages of people's Erdos number, right? Your Erdos number is 1 if you published a paper with Paul Erdos, it's 2 if you published with one of those people, and so on and so forth. What was that? I think it's 3, but I'm not sure, okay? But again, it's not hard to have an Erdos number of 3 because he published with just about everybody, right? The only problem is that by the time I started working, he was like 90. I mean, he was still publishing. Also, he said he had no home. He just sort of wandered around, sleeping on people's cots and doing papers with them. His whole life was mathematics. And there's a wonderful biography of Paul Erdos. And he also introduced the notion of the book proof. He had this story that God has a book of all the best proofs. And every once in a while, somebody would come up with a proof, and he would say, that's a proof from the book. Right? And there's actually a really nice book called Proofs from the Book, which is basically a collected set of all the most beautiful proofs of things in computer science and combinatorics, which I highly recommend because they are also beautiful. Anyway, they introduced the study of random. They introduced this model where you've got a collection of vertices and you throw in a bunch of edges at random. What happens? There are so many interesting questions you can ask, like you get a graph. Okay, what is its diameter? Is it connected? Does it have a Hamiltonian path? Right? Is it 3-colorable? Does it have a large independent set? All of these questions can be asked about random graphs. And one of the amazing things that they proved is this thing called the threshold property, which is basically that all of these questions, initially the answer is no, let's say, depending on how you frame the question. And then there's this very sharp threshold probability or number of edges. And right past that threshold, the answer flips to the other one. The answer flips, right? And it's incredibly tight. Like, just below the threshold, you are almost certain that the answer is no. Just above the threshold, you're almost certain that the answer is yes. So, for example, in the threshold for connectivity is n log n edges, is probability log n over n for an edge. Anyway, I could go on and on about this because it's so beautiful, but let's come back to cuckoo hashing. So this is an example of a random bipartite graph, which is not the most natural basic case there. The most natural place to start is just with regular non-bipartite graphs and all edges being possible. But here we only look at the crossing edges, and we can ask these sorts of Erdos-Renyi questions. So now that we've turned this into a graph, what does a cuckoo hashing failure look like? What could make things go wrong when we try and do cuckoo hashing? Yes? Okay, so yeah, let's start with this at minimum. If the edges that you've put in form no cycles, then I claim that your cuckoo hashing situation is very good, right? And just for now, let me sort of step back and not think about the eviction process, but just say, if you put all these edges in, is there a way to assign each edge to each item to one of its 2 buckets so that everything is happy, right? So how might we think about that assignment process? Well, one natural way to do it is to just direct the edges, right? I mean, I don't direct the edges when I pick them, but if I have a set of edges and I choose a direction, I can basically say that each arrow is pointing to the location of the item, right? That the item goes where the head of the edge is. Okay? So if there are no cycles, I claim that it is possible to put all of the items into different buckets. What is that saying in the graph language? Yes? Exactly, right? If there are no cycles, you can orient, and that is the technical term, the edges such that the in-degree is at most 1. Right? In-degree at most 1 means only one edge is claiming every vertex. How do you do that orientation? Well, what does it mean to have no cycles? Well, no cycles means that all you have are trees. Right? If you have trees, you can root the trees and orient the edges downward. Right? And you're done. Right? Every vertex has an edge coming from its parent, if it's in a tree, except the root, but no vertex has two parents. Right? So, great. If we have no cycles, we're in great shape. Actually, we can say a little bit more. Is a cycle bad? Yes.
Like, if you have a cycle itself, it's not bad because like you can still like for each edge like orienting in a consistent way. Or if you have a cycle and you connect to some edges, it's still fine. But as soon as you have two cycles in a single component, that's the issue.
Great. So this is the thinking, right? If you just have a cycle, fine. Just orient all of the edges cyclically, and they're all happy, right? If you have paths hanging off of the cycle, right? You have a cycle, and you have a bunch of trees hanging off of the cycle. This is what is known as a pseudo-tree in graph theory. And you can essentially treat the cycle as the root of this thing, right? So remember that when we had only trees, the root didn't have any items in it. Everything was, right? So you basically point everything off the root, away from the root, so that none of the tree edges need to use the cycle, and then you do your favorite cyclic orientation of the cycle, and everything works out fine, right? So a pseudo-tree is also fine. You only get into trouble if you have a shape like this, right? Two cycles with a path connecting them. What do you suppose is the technical name for this shape? What if I add a few more trees hanging off of it? What's it called? Yes? Cactus is much more general than this. Is my drawing that bad? I guess it is. Yeah? Exactly. What else could it possibly be called? Okay. So this is a bicycle. And bicycles are the thing that block cuckoo hashing from succeeding. Okay. When I was a graduate student at Stanford, I once picked up a journal, which was 120 pages long, and it only had one article in it. The article was by Don Knuth, a name you should recognize, and somebody named Boris Patel. And they took 120 pages to show the threshold for the emergence of a bicycle in a random graph. Right? What I just said before about thresholds, there's a specific probability at which the presence or absence flips with high probability. And they used this 120-page article to analyze exactly what that threshold is. And so essentially, they were analyzing tightly what goes on with cuckoo hashing, except they were looking not at bipartite graphs, but at general graphs. And you can really use a general graph for cuckoo. Using a non-bipartite graph for cuckoo hashing is kind of like saying you have just one array, and you pick two places in the array, instead of saying you have two arrays and you pick one place in each of them. This is cleaner for presentation and analysis because you don't, if you're using only a single array, you don't want to have the two hash functions hash to the same bucket for a single item. So you have to do like special casing or messy details. Working with bipartite graphs lets you avoid that. Okay? So the basic story for consistent hashing is that you are fine until there is a bicycle. Now, analyzing the presence of a bicycle is a little messy. And it doesn't actually buy you that much. The bicycle happens pretty much at the same time as one cycle. So let's just talk about the probability of a cycle appearing when we throw m edges into an n plus n bipartite graph. Okay. So how do we figure that out? Well, you try not to be too clever in randomized algorithms. Brute force is often a good solution. Okay? So let's ask about the probability of a particular cycle of length k has all its edges chosen. Okay? How do we figure that out? Yes? Would I want to start with m choose k? I mean, so you're sort of saying, let's look at all of the m edges that I'm inserting and ask which k of them land in the cycle. I could do it that way, but I think that's going to be more complicated than I need. Let's look at let's look at the edges of let's focus on the edges of the cycle instead of the edges that we're inserting. Yeah? Let's not do that yet. Let's look at a particular cycle and just ask about that one. What's the probability that that one gets occupied? Right. So that's the starting point, right? So we are throwing m edges into the graph, right? The probability that my m edges miss a particular one, you have to be a little careful because they're all going in independently. Probability that my m edges miss a particular, or my m items miss a particular edge is, well, there are n squared edges. So each of my items has to pick a different edge than the one I'm thinking about, and that has to happen m times. Yes? So that's the probability that I miss a particular edge, and I'm going to say this is approximately 1 minus m over n squared. So the probability that I hit a particular edge is about m over n squared. Yes? Now, I've hit this edge. Now I need to look at all k edges of the cycle. Now, there's a little bit of dependence, right? The fact that I hit the first edge of the cycle means that one of the items is there, and so it can't occupy a different edge of the cycle. But that's, just one of the m edges, so it doesn't change things very much, right? So I'm waving my hands here because I know that you can sort of work out the approximations. I claim that the probability that I hit all k edges of the cycle is approximately m over n squared to the kth power. Right? This is not exactly true because these events are not independent, but the overlap between them is so small that it's close enough. Yeah. Yeah. So that's the point. It's an upper bound. Okay. Because the fact that one edge got occupied makes it less likely that your edge gets occupied. Okay. All right. So that's the probability that a particular cycle gets occupied. How many cycles are there? Well, the number of cycles of k edges is just equal to the number of cycles of k vertices, right? And I basically just need to read off a sequence of vertices. And I shouldn't have repetitions, but I'm not even going to worry about that, right? Basically, there are n choices for each vertex on the cycle, leaving out a couple to avoid repetitions. And I need to pick k of them in order, right? So the expected number of full cycles is equal to n to the k times m over n squared to the k, right? And this is just equal to m over n to the k, right? But this is also, by Markov, this bounds the probability of any full cycle of length k. Yes? And now I just need to sum over all possible values of k, right? I need to worry about cycles of length 2 and cycles of length 4 and cycles of length 6 and so on and so forth. So the probability that I get any full cycle of any length is at most m over n squared plus m over n to the 4th plus m over n to the 6th, and so on and so forth. Yes? Question? Yes. So this would be a cycle of length 2. And that's included in the analysis. Okay. So essentially, you can see, right, what we have here is a geometric sum, right? As long as m is less than n, this geometric sum is going to be small. Right? So until m equals n, you are unlikely to have a cycle. Yes, a question. Well, that's a very interesting question, right? And let me hold that for once, because I'll talk about refinements of cuckoo hashing in just a minute, but let me just finish this story first, okay? So what we've proven here is that if, m is substantially smaller than n, then we're unlikely to have a cycle. If we don't have a cycle, everything is trees, then there's a way to orient the edges so that everything fits with no collisions, right? You can do the same analysis, and you can look at it in the notes, to argue that in these conditions also, every tree is small. You're not going to have any large trees. You're just going to have little pieces of tree. Okay? And why is that useful? Because that tells you about the behavior of the insertion algorithm. Right? So I'm going to wave my hands about this so that I can get to the other thing I wanted to cover. It's worked out in the notes. But think about doing an insertion. Right? When you insert an edge, it maybe joins a tree and forces evictions. What are those evictions doing? They're flipping some of the edges in the tree. So you're basically going to walk over the tree for a while, flipping edges, and possibly flipping some of them back if you get stuck, right? But you'll stop after you traverse the entire tree. You will have finished. You will have at that point flipped all of the edges properly. So the time that it takes to do an insertion into the cuckoo hash table is proportional to the size of the tree that you encounter. And you can use exactly the same trivial union-bound analysis to say that the trees are small. And therefore, the insertions are fast with high probability. So this is nice from this is not amortized, right? This is a nice worst case hash structure. Okay, as long as you don't grow beyond the the limit of putting n items into it. Okay? And if you dive deeply into the theory of random graphs, what happens is that as m gets really close to n, the tree suddenly starts to get bigger and bigger and bigger. There's this emergence of something called the giant component in the theory of random graphs. And so you end up with this gigantic tree, and eventually it's really huge and your insertions are getting really slow, and shortly after that you get that cycle that breaks your tree. So there's this very beautiful evolutionary analysis of random graphs that comes into play here. Okay? All right. You asked a very interesting question about what happens if you get stuck, or right, when you do have one of these cycles. And there are a couple ways out of it. One way, which shouldn't surprise you given Wednesday's lecture, is to look in more than 2 places. Okay? You can generalize cuckoo hashing to say I'm going to look in 3 locations, or 4 locations, or 5 locations, right? And by looking in more locations, you create more ways out when you have these congestions, and you can push the load factor of the hash table higher and higher, right? What we're saying here, that you can have m items, that m can be about n, that's giving you a load factor of 50%, right? Because there's 2n space in the table and you're only putting n items into it, right? As you go to 3-way, 4-way, 5-way cuckoo hashing, you can push the load factor higher and higher, okay? Another approach that you can take is literally what you said. If your edge completes a cycle and won't fit, you just don't put it in. You keep something on the side for these edges that don't fit. And you can prove that there's only going to be a few of them. And so the algorithm is, use the cuckoo hash table for most things, and then use this check this collection on the side for the few items that aren't fitting in the cuckoo hash table. And you can prove that this allows you to take the load much higher without really impacting your lookup time, because there will only be a few items held out on the side. And you're going to do that in your homework. Okay? All right. Any other questions? Okay, let's take a break. I want to show you one other weird hashing trick before we finish today. But break first. All right, everybody's sitting, so I guess I'll start again. One last detail I forgot to mention about cuckoo hashing is that, as I said at the beginning, you don't need full independence. People have shown that a log n way independent hash function, a generalization of the 2-way independent hash function that you used on Wednesday, that a log n way independent hash function supports the same analysis as we just did. There's also a somewhat weird variant of cuckoo hashing where you only need to use 6-way independent hash functions. But you have to use 6-way independent. Like, you can't use 5. The last weird hashing story I want to tell you about is something called consistent hashing. And I basically want to tell you this story as, first I want to say, nobody came to my country line dancing class from here. I had a very full house, but none of you came, so you should come. Sundays, 5 to 6:30 in the Wellness Lab of the Student Center. But consistent hashing. And the reason I put this here is that I feel it's a wonderful story to tell people about why you should study theory, even if you're not a theoretician, or at least why you should talk to theoreticians. So consistent hashing was developed because Tim Berners-Lee, who invented the World Wide Web, was worried about flash crowds on the web. What happens when I don't know if anybody still reads Slashdot, but back in the day, there was a phenomenon known as getting Slashdotted, which is where your website somebody would write a post about it on Slashdot, and all of a sudden, Slashdot's hundreds of thousands of readers would all visit the website. And that poor website would collapse under the load. Tim Berners-Lee was worried about what can we do about these flash crowds. And one of the answers is to try to spread the load by taking the content on that website and spreading it around to other machines that could serve it. And that way, instead of having everybody go to the same machine, people would be going to all these different machines in order to try to fetch that content, and none of the machines would collapse under the load. So we have a load balancing problem. We've got n different machines, and we want to, instead of putting the content on one machine that's going to be too popular, we want to spread that content around these n machines in a sort of load balanced way so that no machine gets hit with too many requests. Okay? What would be a natural technique for taking a web page, say, and deciding which machine you want to put it on so that people can find it, but no machine gets too many web pages or too many of the popular web pages? Yeah? A hash function, right? Take the URL, right? Think of your n machines as your n buckets. Take your URL, hash it. That tells you which bucket, which machine is responsible for serving that particular URL. Okay? Great, except that has a problem. And this is a problem that I and Tom Layton and a few students, Danny Lewin and Eric Lehman, got from Tim Berners-Lee. He said, what can I do to make this work? Because regular hashing has a problem, which is that our buckets in our hash table are always there, but machines crash, right? So you hashed your page to machine number 17, and somebody just drove over machine 17 with a digger, and it's no longer on the internet, okay? So we have a problem, which is that buckets can disappear, and they may also reappear, right? Machines are coming and going all the time. So we need a hash function that will allow us to change, to add and remove buckets and still maintain load. Now, there's some obvious limits to this, right? If you want to be able to, if you're going to remove a bucket, obviously you have to reallocate the stuff in that bucket to other buckets, right? So if there are n buckets, each bucket is going to have about 1 over n of the stuff. So when you remove a bucket, you're going to have to move 1 over n of the stuff. Similarly, if you add a bucket, if you add your nth bucket, if you want to rebalance things, you're going to have to move 1 over n of the stuff to the new bucket, right? But let's think about what would happen if you used a regular hash function, okay? Like our favorite, we take our URL and we map it to AU plus B mod n, right? Okay, so I've got my n machines indexed 1 to n. Now I want to shrink so that I only have n minus 1 machines. So now instead of doing AU plus B mod n, I'm doing AU plus B mod n minus 1. What happens? Yes? Yeah, just about every single item is going to need to move to a different bucket. So all of a sudden, one machine goes down and you have to rearrange the entire internet. Right? That is not a good way to distribute your content. Right? What we want is a hash mechanism that is consistent, right? That removing one bucket only causes a shift of a little bit of your information. And adding a bucket only causes a shift of a little bit of your information. Okay? And so this is the problem that we were posed. And it turns out that it has an answer. Let me show you the technique. And on Monday, or sorry, yes, it's Friday. On Monday, we will do the analysis. So the method is to make a ring. Notionally, think of this as the unit interval folded back on itself. Okay. Hash each item to the ring, and also hash each bucket to the ring. My hash function, again, I'm assuming is just a random value, a random number in the 0, 1 interval. And now I also hash my items to the ring. Okay. And I just assign each item to the immediately, which way do I do it? I just want to be consistent with my notes. Immediately following it on the ring. So basically, all of these items go to this bucket. All of these items go to this bucket. All of these items go to this bucket, and so forth. Okay. So I can already argue to you sort of intuitively that this is going to do well, right? So what would you say is going to be the load on a typical bucket? Or what determines the load on a typical bucket? Yes? Yes, exactly, right? What determines the load on this bucket is how much of the ring is present between this bucket and its predecessor, right? Because all the items that land in this interval are going to be assigned to this bucket. But it should be intuitive, and I'll prove it on Monday, that the size of this interval, well, its expected size is 1 over n by symmetry, and we're going to show that its actual size is not a lot bigger with high probability. So each bucket owns a relatively small portion of the interval, and therefore each bucket only receives a small fraction of the items. So the load is balanced. Okay? Now, what happens when a bucket leaves? What do you have to rearrange? Yeah. Exactly, right? When this bucket leaves, it can no longer be responsible for the stuff directly behind it, but that just means that that stuff has to go to the next bucket. Yes? So we just argued that this bucket was only responsible for a little bit of stuff, and only the stuff in the departing bucket needs to be moved to one other bucket. So only 2 buckets are involved in the shift, and you're only moving a small fraction of the stuff that's spread out over the ring. Similarly, if a bucket arrives, it just takes over some of the content of its successor. So again, only 2 buckets have to be involved in the negotiation in the reallocation, and the amount that's reallocated is proportional to what's owned, which is, again, a small part of the ring. Okay? Yes, question? Both hash functions are fixed, right? You pick one global hash function, and you use that to hash the buckets and to hash the items, and you never change it. Okay. I should be like, we were just talking about how when n changes, when n doubles, you might need to do things. I've cheated my way around that by talking about hashing to the unit interval, right? Which gives you an infinite number of bits of precision. And so it doesn't matter how many buckets there are. Geometrically, what you're doing still makes sense. In practice, you'll want to have only a certain number of bits in your hash function. And if it's too few, you're going to start getting confused collisions. And if you get too many items, you're going to need to start adding more bits to your hash function. Okay? We'll worry about that a little bit on Monday. Yeah? Well, the problem is that if putting buckets deterministically kind of puts you into this situation. Oh, I see what you're saying. So if I put buckets deterministically, right, you're saying space them out evenly? Okay, but think about this. If I remove a bucket, they're no longer spaced out evenly. So I'm going to have to, if I want to preserve even spacing of the buckets, I'm going to have to move all the buckets by a little bit, which is going to force me to shift all the, so I'm going to have to involve all of the machines on the internet in reallocating content. It might not be a lot of content, but they're all going to have to be involved in the conversation. Okay? Also, there has to be this global awareness of how many machines are present, right? Another powerful thing about this technique is that it's local, right? Each machine needs to know where it belongs, and it basically needs to know about its predecessor and its successor, and it doesn't have to ever talk to anybody else. Okay? All right, so I'll get into this more on Monday, give you sort of proofs and details. There's a homework problem that depends on this, so sorry about that. Sorry for spilling that over, but we'll take care of that on Monday. And I will see you then.